Okay, so our last video here is on artificial transmutation and um, the uses of nuclear chemistry. Okay, so to start off with artificial transmutation, we want to talk about that word transmutation. Okay, we know this means changing a nucleus of one element into a new nucleus of a new isotope. Okay, so we've done that in the past through natural decay, where something that's naturally radioactive undergoes alpha, beta, positron decay. However, we can get stable nuclei to change, to transmutate, okay? Or we can actually speed up the process through artificial transmutation. This is where we have a high speed collision of particles forcing a stable nucleus to break down, or forcing something that is radioactive to break down much, much faster. So in this case, I have a stable nucleus in nitrogen 14, totally stable, totally normal, being collided with by an alpha particle. Remember, 4 over 2He is an alpha particle. Okay, don't forget you can look at table O to look at the notation for alpha particles and protons and things like that. And now my nitrogen is going to change into oxygen 17 and a proton thanks to that collision. Okay, now this has to happen at very, very, very high speeds, but it can allow for a nucleus to change. Okay, an obvious way of seeing that you have artificial transmutation is by seeing that you have two reactants on the left side of the arrow. Okay, you have the arrow in the middle of your equation. If there are two things to the left of it, okay, you have artificial transmutation. Okay, where in natural decay you only ever have one. One specific type of artificial transmutation is fission. Okay, fission is a large nucleus, is split into two smaller nuclei. Okay, in this case, I have uranium 235 being collided with by a neutron and breaking down into krypton 90 and barium 143. You can see that in the equation. You can also see it in this little diagram off to the right. You also see that three neutrons get produced when this happens. So when those three neutrons get produced, they're going to collide with a new uranium atom, okay, and force this to happen in that uranium atom. Okay, this creates a chain reaction, okay, which is eventually can release lots and lots of energy. Okay, now along with that energy, though, we get a lot of nuclear waste. Fission is currently used in nuclear power plants and in the atomic bombs. Fusion is kind of the opposite of fission. This is taking small nuclei and combining them to form a larger nucleus. Okay, so you're taking two nuclei and making one new nucleus. So in my equation down here, I have two helium nuclei forming a beryllium nucleus. Okay, they join together. In my example in the diagram down on the bottom here, I have a hydrogen 3 and a hydrogen 2 forming a helium-4 atom. Okay, lots and lots of energy is produced through fusion as well, just like fission. We'll talk about how in a second. Okay, and there's no nuclear waste produced, but this is very, very hard to control, and you need extreme heat to start this reaction. Okay, where do you see fusion? You see fusion on the sun. That's what powers the sun. Okay, on Earth, okay, we do have fusion bombs. Okay, they're called H bombs, hydrogen bombs. Um, and fusion reactors are starting to be developed, but really are not controllable quite yet. So, where does the energy in fission and fusion come from? Why do we get so much energy? Well, it comes down to the famous equation E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is a constant. This breaks Anton Lavoisier's law of conservation of mass because we're taking a very, very, very small amount of mass, not really a measurable amount of mass in terms of what we look at, but if you go down further in terms of physics, you do see a little bit of mass turning into quite a bit of energy. Okay, um, this happens in both fission and fusion. Okay, where a little bit of mass is turned into a lot of energy. Okay, some of the uses of nuclear chemistry. We use it in industrial measurement. For example, we can see how thick something is by seeing how many beta particles can pass through it, okay, or alpha particles or whatever. Um, so that's something that may come up. Radioactive dating, okay, something you talked about in earth science. Okay, uranium 238 has a half-life of over 4 billion years. It's used to date rocks and other very old space objects. Okay, space rocks mostly. Carbon 14 can be used to date things that were once alive. Okay, its half-life of 5,730 years, give or take, um, is good for dating things back to a few hundred thousand years ago. Okay, things that may have been alive, but they have to have been once living because they have to have that carbon inside of them. Uh, chemistry, nuclear chemistry is also good in nuclear power. Okay, we have nuclear power plants that provide electricity to many people. Sterilization of food, okay, killing bacteria, things like that. Very big in the medical industry, okay, as tracers, okay, where we can follow the radiation emission through the body. And in a similar way, we use them in pipes and industry to detect leaks. In radiotherapy, they're used to treat cancer. Cobalt 60 is a very common one. Iodine 131 is used to treat thyroid cancer. Okay. Um, I've also seen nuclear chemistry used in old school um, smoke detectors. Okay. To help detect the smoke, they're sending out certain particles through nuclear decay. Okay. And there are other uses as well. Now, these are all very common uses, and some of them, you really should know uranium 238, carbon 14, cobalt 60, iodine 131. You should be able to recognize those. Okay, but there are also just inherent dangers and advantages to nuclear chemistry, nuclear power in general. Okay, we also know about bombs, nuclear bombs. It's something that people have are afraid of. Okay, that nuclear power can do so much damage very quickly. We've seen it in history. So we know that nuclear chemistry can be very useful in all of these ways, but it also can be dangerous, right? So nuclear power produces tons of electricity, no carbon emissions. Okay. But you also get lots of nuclear waste. You also have the danger factor with it, right? You look at things like Chernobyl, and you can see what happened there. Um, as much as nuclear chemistry can be used to treat cancer, okay, the way that DNA can mutate to create cancer cells is oftentimes from radiation due to radioactivity. Okay, so there's a lot of different advantages to nuclear chemistry and disadvantages as well, and we're going to talk about those, and you guys will discuss those in class as well. Okay, so that's it for this video, and this will be the last video for nuclear chemistry.